Today we're tackling a core concept that, honestly, strikes fear into the hearts of chemistry students everywhere. And we're going to completely reframe it. Instead of treating organic chemistry as this dreaded, endless list of reactions you just have to blindly memorize, we're going to look at it as a highly predictable, logical stage play. And the best part? It only has exactly 2 characters. Once you understand what motivates these characters, the entire subject literally transforms from a memorization game into pure, beautiful logic.
Okay, let's dive right into this. That quote right there, it perfectly sets the stage for our entire discussion. Now, if you've been following along with the foundations of chemistry, you already know all about our electron-rich character, the nucleophile, right? The one that's just super eager to give electrons away. But today, we're turning the spotlight entirely onto the other half of this dramatic duo.
So, here's our playbill for today's explainer. 1. Meet the electron seekers. 2. 4 causes of electrophilicity. 3. Reading reaction mechanisms. 4. Forces modulating reactivity. And 5. Putting it all together.
Part 1. Meet the electron seekers. Meet the electrophile. By definition, this is the electron-poor, electron-seeking species. Think about it like this. If the nucleophile is the character eager to give, the electrophile is the character driven by a deep, literal hunger to receive. This intense hunger for electron density is the actual engine driving most organic transformations. And I really want to emphasize this point. Understanding why an electrophile behaves this way is infinitely more powerful than just memorizing some textbook definition.
Part 2. 4 causes of electrophilicity.
An electrophile's reactivity isn't magic, and it's never just arbitrary. It always traces back to one of 4 structural causes. And this brilliantly illustrates what they are. First up, we have a formal positive charge. This is a direct, undeniable deficit of electrons, like a bare proton or a carbocation. It's basically an outright invitation for electrons. Second is bond polarization. This is where a difference in electronegativity literally pulls electron density away from an atom, leaving it partially positive. Third, we see an incomplete octet, like in boron trifluoride, where the molecule physically lacks a full set of electrons in its skeleton. And fourth, polarized pi systems, such as a carbonyl group, where those pi electrons are being drawn toward a highly electronegative atom like oxygen, completely exposing the carbon.
So instead of trying to memorize a massive, overwhelming inventory of molecules, let's give you a diagnostic superpower. Whenever you look at a molecule, just ask yourself these 3 simple questions. 1. Is there a formal positive charge? 2. Is there a visibly polarized bond? Or 3. Is there an incomplete octet? If you can answer yes to any of those 3, boom, you've successfully identified an electrophilic site. It really is that simple.
Part 3. Reading reaction mechanisms.
Now we need to understand the incredibly strict script these characters have to follow. In chemistry, we call this the reaction mechanism. I want you to think of the curved arrows in a mechanism strictly as a camera tracking electrons. That arrow absolutely must start at a source of electron density, like a lone pair or a pi bond, and it points directly toward the electrophile. Starting an arrow from an atom itself or from a positive charge is a fundamentally incorrect script. Atoms don't move on their own. The electrons do the moving.
Part 4. Forces modulating reactivity.
Okay, identifying the characters and knowing how our camera moves is only part of the story. Now we introduce our stage directors. These are the underlying forces that dictate the final outcome of our play. The first director is electronic effects. These dictate exactly how charge is stabilized. You've got the inductive effect, where groups physically pull density through sigma bonds. That's exactly how 3 chlorine atoms turn standard acetic acid into highly acidic trichloroacetic acid. Then you have resonance, which seamlessly spreads charge across pi systems. And finally, hyperconjugation. This perfectly explains why a tertiary carbocation is just so much more stable than a primary one.
Our second stage director, steric effects. This is all about physical crowding. You see, even if a reaction is electronically favorable, it's going to be blocked if the atoms simply cannot physically reach each other. A methyl group is wide open, so it reacts incredibly fast. But a tertiary substrate? It's so structurally crowded by these bulky groups that the concerted one-step backside attack required for an SN2 mechanism is just completely shut down, no way around it.
And our third and final stage director is the solvent effect. The solvent isn't just some passive backdrop, it totally dictates the action. Protic solvents, like water, form hydrogen bonds that surround and shield small anions, basically dampening their reactivity. But aprotic solvents, like DMSO, they can't hydrogen bond the same way. They leave the nucleophile completely exposed, essentially naked and highly reactive. Notice how this completely inverts the reactivity order. In a protic solvent, iodine is your absolute best nucleophile, but switch to an aprotic solvent and suddenly fluorine takes the crown.
Part 5. Putting it all together. Let's move to a real-world scenario and see how this all builds together. Here we are contrasting two cases using identical leaving groups, bromide, but under totally different stage conditions. In case A, we have methyl bromide and DMSO. It's electronically favorable, sterically unhindered, and the solvent leaves the nucleophile completely exposed. The result? A lightning-fast SN2 reaction. But contrast that with case B, tert-butyl bromide in water. Here, the severe steric hindrance totally blocks the backside attack, and the protic solvent stabilizes a carbocation instead. These stage conditions literally override the electronic principles, forcing a completely different multi-step SN1 pathway.
Now, what's really fascinating here is how we can see this climax play out side by side. For the first case, we get a beautiful, single-step concerted backside attack, simply because the stage allowed it. But for the second case, it's a slow, stepwise process, literally just waiting for the leaving group to depart to form a stable tertiary carbocation. This proves conclusively that you cannot just look at the electrophile in isolation. You absolutely must look at the structural and solvent environment to predict the correct mechanism.
And that brings us to the big picture. If you take away just one thing from this explainer today, let it be this equation. Every single mechanism is simply the story of electrons moving from a nucleophile donor to an electrophile acceptor strictly under the direction of the stage conditions. The sterics, the electronics, the solvent. Grasping this single recurring story is the real superpower. It takes an endless textbook of disjointed chemical reactions and turns it into one beautifully predictable narrative. So to wrap things up, I want to leave you with a quick challenge to test your brand new diagnostic superpower. Thinking back to case B, the heavily hindered tert-butyl bromide in water that was totally forced into an SN1 pathway, which single change, either to the substrate itself or to the solvent, would most efficiently force that reaction back into a fast, one-step SN2 pathway? And more importantly, why?